discuss the MATLAB code for simulating the partial differential equations for water waves. For simplicity, we'll only look at the linear water wave equations. Alright, so here I've loaded up the code into MATLAB, and let's just see what the results are, and so discuss what the aim is. So here I've just run the code that we see here, and it's generated the graph on the right here, and this is a plot of the water surface in the simulation. Now you see space runs from 0 to 10 across here, time runs from 0 to 5, and the simulation started with the water surface flat at a height 0. And then what happened, at time 0 we started to generate a wave by setting u at x is equal to 0 to be oscillatory with at an amplitude of 0.3 sine 5t. And the other end, the velocity of the water has to be 0 horizontally. So what happens here, we start generating waves. The wave propagates across this pool, reaches the other end, and then reflects back across here. And as that wave travels back, it interacts with the second generated and the third generated waves, so that eventually we see some nice complex waveform. Now, the other thing we've done here is not only plot the height of the water surface, we have also cunningly coloured the water surface with the other field in the partial differential equations, the velocity u. So the colour here depends upon u, as indicated by this colour bar. So the dark blue is u being minus 0.3, ranging to green, which is about 0, up to the red, which is plus u of plus 0.4. So you can see u is essentially to the right at the peak of the wave and to the left at the trough of the wave. Okay, so how do we compute this figure? The algorithm is a modification of our basic template for simulating PDEs. So let's have a look at it. And the main modification is to cater for the staggered grid we use, because this is a pair of first order differential equations in a very special form, but one which is relatively common. So we need some global variables, and we'll describe those variables as we go along. So firstly, g is the acceleration of gravity, which at 9.8 is near enough to 10 for our purposes. As always, we specify the number of points at which we're going to have grid values, and this is here it's 41. As you can see in the output, there's 41 grid points in X. And although if you count, you'll only see 20. We'll come back to that. It should be odd here, the number of points, because the boundary conditions are that u is specified. And so the grid of interleaved unknowns has to start with a u and finish with a u, which means it has to be an odd number of points. Okay, the domain of computations is from x between 0 and 10, and we get a nice even grid by using the linspace command. Then one of the things we need to do is to define the depth. So it's linear but varying depth. So here we specify that the depth is 1 plus 3 times x over the very last x value, which is 10. So in other words, the depth here varies linearly from 1 at x is equal to 0 to 4 at x is equal to 10. And because it's varying depth, the waves vary their properties as they propagate across the domain. And you can see that in the solution, although it's not all that apparent here. But let's rotate it, rotate this graphic, and you can see in this first wave, for example, that it's curving as it propagates from x is equal to 0 to x is equal to 10, and it curves because waves in water travel faster in deeper water. And so the wave's travelling faster here than there, so it changes more in x per unit time than it does here. And the same for all these others. Now, the depth is also a global variable, just as is x. Then we need some other global variables. We need the index of the interior points at which we compute a value of u. And these are the odd index points, as we have commented. We also need the index points of all the grid points at which we compute a value of the free surface eta, which in the computer code is denoted by h. So coming back to this figure here, what we saw in the mathematics, in the algebra of the mathematics, is we deal with a grid which is indexed by half integer j, and we talk about points x and a half, eta 1, u 3 halves, and so on. But in the computer doesn't deal with half integer indices. We have to have integral indices. So in the computer, indexing is as in the bottom half of this figure. And you just have to keep in mind the relationship between the two, that the computer index is twice what we do in mathematical algebra. Right, and these are the integer indices. Okay, then as usual, we have to specify some initial condition for the integration, v0, and as I said, we started out with a flat surface and also zero velocity, which I didn't say. And that's obtained by having 0 at every point x on the grid. Then the next point is simply to invoke ODE15S to integrate the differential equations forward in time. And the differential equations are coded in dv by dt that we'll look at shortly. We tell it to integrate over a time from 0 to 5, as you saw in the picture. And we give ODE15S the initial values of the initial conditions at the interior points. And that's that vector. All right, and what it does for us is it computes values of time t, for which it determines what the values of u and eta are, and it returns those values in v. Right, now what do we do to plot? Well, it's the usual sort of thing. Remember that we adjoin to either end what the boundary values are, so that this v is the interior values, but this v is the interior values and the boundary values. Now, the new feature here is that we do not plot every time step. So if we plotted every time, then this picture would be dominated by lines, black lines running across here. It would be very hard to see things. So quite often we need to plot a subsample of what is computed. And a straightforward way of doing that is to do it like this. We create an indexing vector, say I, of a subset of the times. So instead of plotting all times, we'll plot time 1, time 3, time 5, 7, 9, etc. And this construct generates that indexing vector. Okay, so we then draw the surface pretty much as before, except we're only going to draw the values corresponding to the points of the surface height. So that's x, jh. We only plot at times ti that we specified here. And so we only plot the surface values at those points, v at times I, and corresponding to the places where there's a water surface height value. Now, the extra ingredient to this surface command that we haven't seen before is this fourth argument. This fourth argument plots the colour that's used in the graph, and we want the colour to be the velocity, and at each h point we don't have a velocity value, so what we'll do is simplify it by saying plot the velocity just to the right of each of the h's, and we get to the grid point just to the right for each h grid value by adding 1. Then, as usual, label the axes, draw the colour bar so that we can see over here where the velocities go from and what the colours mean, and then, as usual, get the best quality copy of that for inclusion in reports using the print to encapsulated postscript with colour. That's what that mysterious acronym means there. Okay, so now the remaining challenge is, what about the time derivatives? The function dv by dt that ODE15S integrates. Well, it has to start in this form. We have to compute a vector of time derivatives for any specified time t and for a given vector v. Now here there's no dependence upon t's, it's only upon what is v. We access the global variables, then we compute the space step of the grid. Right now, here on a staggered grid, remember that, here's the graph, the natural spacing is from one point, say x2, to the next point, x3, skipping over one point in the middle, and that's what we call delta x. And that's what we use in the differentiation formula. Okay, so delta x is x3 minus x1. Okay, then as usual, v, the ODE15S deals with is just the interior values. So to get a full vector v, we put in the u boundary value on the left and the u boundary value on the right. And now we have to compute the time derivatives. But there's two sorts of time derivatives. There's the time derivative of the water surface height and the time derivative of the velocity. So it's easiest to compute them separately, and to compute them separately we want some place to put them, and so it's easiest to define some place to put them. So we'll put them into a vector vt, which is of size x, so it's got an element for every x grid point, and the safest way to initialize such a vector is to initialize it to nan, which means not a number. What happens then is if you make a mistake with your indices, you'll find out about it. Okay, so then the differential equations. So the first one is d eta by dt is minus d by dx of the depth times the velocity, and d by dx is done by finding the depth and the velocity one grid point to the right of each h point, and at one grid point to the left, taking their difference and dividing by delta x. Right, so what we're doing in essence, come back to this graph, is say d eta 2 dt is dependent upon the difference between eta 5 halves and u 5 halves and u 3 over 2 divided by delta x. That's all we're saying. Now in the computer we get from eta 2 to u 5 halves and u 3 halves by adding 1 to the index and subtracting 1 from the index. And we do that for each j h. And so that's what happens here. So djh plus 1 is the grid point immediately to the right of jh. Vjh plus 1 is the grid value immediately to the right of jh, and that grid value is a u value. Similarly, this is the depth immediately to the left of the current grid point. And this VJH is the grid value immediately to the left of the H grid value, and so it's the U value that's immediately to the left. Okay, so that's the derivative minus d/dx of du. Similarly for du by dt, it's minus g d eta by dx. How do we get eta? Well, it's the grid value immediately to the right minus the grid value immediately to the left, because the grid value immediately to the right is a eta value, and the grid value immediately to the left is the neighbouring eta value to the left. Then for ODE 15S, we only give it the interior values, and this statement says out of all the vector vt, which is the entire vector x, we only want the interior values, and so just ask for 2 to n minus 1, and that gets sent back to ODE 15S. Okay, the only thing remaining is the boundary values, and these are exactly as before. We just create a little function that computes them. So in this problem, the leftmost boundary value was that u was generated by some oscillatory wave maker, 0.3 sine 5t. That was this oscillation there. And the right boundary value of u is 0. And that's what's going on here. It's not apparent because this is the water height, but everywhere along there, u is 0. Okay, and that's how the code can work. If we want more accuracy, you can increase the number of points, say 81, and run it again. And it's finished, and there you see a lot more points.